Thank you very much for coming here. We decide to have this kind of name in order to remember a famous computer scientist of the ancient Greek that I will quote in a few minutes. Let me tell you a couple of words about us. We study in Sapienza. I'm a statistician and he's an engineer. And we also do a little bit of reinforcement learning research together. And yes, we are also roommates, which makes all the thing fairly difficult. So to get an idea, how many of you knows about reinforcement learning? Wow. How many of you played reinforcement learning? So I built some bunch of stuff, try to apply reinforcement learning to some problems. Oh, okay. So you know how hard it is to get it done. Okay, good. Okay, so the talk is going to be a little bit technical. There might be some points in which, I don't know, it can get technical. So please, maybe write down the point. We'll be happy to answer to your questions at the end of the talk, or stop us right after and we'll dive into every detail you wish to talk. All right, let's start. So we're gonna go through the math behind Go, and then we'll see how the software in Go is built down to AlphaGo. And then we'll get into the detail of the method from policy iteration down to the code. As you can see, this part is split in two big chunks. One is very boring, and the other one is very fun, and the fun part is going to be his job. Shall we begin? Okay. So this is the famous Greek. We believe that, for a true AI, isn't measured by the size of the tree, but by the precision of its move. And I don't know if you remember this quote, but it comes from Hercules, which is fairly known. What is important? Well, because that's exactly what made AlphaGo win. Let's see how. So the game of Go is a very simple game to some extent. It's played on a Go ban, which is a board. It's a 19 by 19 board. There are two players. One is going to play black stone, the other one white stone. You start usually with a black one, and at each step you place a stone on the board, and you move on. There are two simple rules. The first one is that if, for example, like right there, the white stones are surrounded by the black stones, they are captured, so you conquer the part of your territory, and the guy is going to have, when the board is full, the guy who has most of the territory actually win the game. Now, how complex it is? Well, the first thing to notice is that Go is a constructed game. What does it mean? It means that you start with an open space and you start building it. You put stones and you build your plans in those while you play. It's not like chess, which is destructive on the other hand. The second thing is also humans say that the game of Go is intuitive. It's much more intuitive than chess, because in chess, if you talk to a player, they actually will tell you, I have this idea as next move. Then there are 10 to 170 possible states that you can cover, and there are 10 to the 360 possible games for each state that you can be in. So the tree that you can build on this game is fairly large. And for what matters to us as researchers, this kind of game is adversarial, which means that there are two players playing against each other. And the other, of course, one wants to kill you. That's why it's adversarial. It's fully observable, which means that we can see exactly what's going on the board at all the time, and that's enough for us to plan the future. And it's deterministic, in the sense that if I place a stone on the board, it's going to be there. There's no probability that the stone will jump somewhere. Good. So AI in Go, it's been a very lasting challenge. After Deep Blue, they use alpha-beta search. They try to apply the same ideas in the game of Go, but the tree is just too big. It's impossible to explore it. And in 2014, they still believe that solving the game of Go was a decade far ahead from the result that has been achieved. This was the software that was before AlphaGo, it's called Crazy Stone, and was the one to introduce Monte-Carlo tree search in searching the space. It also used a linear classifier to do prediction of possible states and a bunch of other heuristics. But then AlphaGo came along, and that was, I think, 15th of March 2016. And one of their main innovation was to use deep learning to do function approximation of value function and policy. Don't fix on those words, we'll dive into that in a bit, but the basic idea is that we just want to use their data and the neural network to get an approximation of this evaluation function, so how good I'm playing. But still the result, and this is we all remember this phase, it was an astonishing moment, AlphaGo win 4-1 with Lee Sedol. Well, actually, it's not there, I didn't know about it, but it wasn't there, he was believed to be one of the best players in the world, but he wasn't the world champion. After some time, like for a couple of months, they played with the world champion in Go, and they, of course, they destroyed him. But what was actually more astonishing is that they said, you know, in order to have an AGI, we want to be able to learn from tabula rasa. We don't want to use data from humans. And they actually did it. And the next version was called AlphaGo 0, and then Alpha 0 because that's been applied to other games. And it learned completely from scratch. They removed any human intervention inside. There is no more data, no more prior assumption, nothing at all. And if you know what is Stockfish, there was believed one of the main chess engine that's been destroyed after just 4 hours of training of AlphaGo, of Alpha 0 in this case, by something like 30 wins over 100 games. Good. So far, so good. So what was the main idea, the main juice behind all of these stories is actually reinforcement learning. Well, if you've been driving a little bit on reinforcement learning, what you'll probably seen this picture, and what you have is that you have an agent that has to play with an environment. So think of you play a game, you see a screen, you press a button, you go to the next screen, and so on and so forth. The more you do this, the more you somehow try to achieve some goals, maybe kill someone or kill the spaceship, and then you collect this reward while you play. A better example is actually is this. I mean, suppose I really want to have an ice cream, but I don't know how. I don't have Google Maps. I cannot have access to the world information. I can only see what's outside. So I'm gonna go outside. I'm gonna walk around until I don't find the relevant information that can tell me where is the ice cream place. And this for me is the reward that I can collect, and will drive me to the Holy Grail, which is this amazing gelateria that is not too far ahead from here, and it's not commercial, but it's really amazing. I love it. Great, now it's clear what reinforcement learning more or less it is. And there are two things to notice in this setting. The first one is that it's the only it's one of the main methods in which the agent chooses what to see. So the agent is able to consciously drive what to see in the environment according to the action that it takes. And on the other hand, depending on the action that it takes, it's going to receive a reward, and it's going to be able to estimate how good it's doing. So it's the one who's shaping what world it's seeing, and if it takes some action, it's not going to see another part of the world. And if it's going to take some action, it's not going to have some specific rewards. Well, this is important. Well, because that's what we want to optimize. Formally, we have a policy, which is a probability over possible actions that you can take. And we have this very bad guy here, which is called the value function. A value function is simply how much juice you collect while you live from time step 0 until you can go in the game. Good. In a more, let's say, Pythonic term, we just have a function that will give us state. It's going to give us back the value of this state. And we have a policy that we give, again, a state, and it's going to give us returnable action that we can play in this state. OK, so then the last, say, now we know more or less what is the framework. What we want to do is trying to understand how do we find a good policy. Well, if you think about it, it's not that complicated. Manuel, what the fuck? Okay, it's not that complicated. It's not that complicated because what you actually want to do is to imagine all possible moves that you can do in the future. So you want to plan far ahead. And for each possible state in the future, you want to find and try different actions that could actually make you win your game. Now, remember that we have 10 to the 360 possible games for each state, so it's fairly complicated, but the idea is that one. you want to imagine, you want to go very far ahead, and for each possible future that you are going to experience, you want to try the action that is going to perform best in that point in time, in that specific state. And that's what polyiteration does. So it's made of two parts. The first part is policy evaluation. So we're going to try to see, given a policy that could even be random, for example, how much juice we can get. And then, according to how much juice we get, we can try to see where, for each possible state, we can try a different action that is going to make us improve our policy, improving our way of behaving. Okay, so policy improvement. How do we do that? Well, we said we want to plan really far ahead. There are many possible states, but we should find a way to somehow plan possibly. And that's what plan to the future and try new actions. That's also the other important part. And that's what Monte-Carlo research does. What Monte-Carlo research does is a method that allows you to do sampling-based look-ahead search, right? More or less. What simply does is that you start from a starting state, and then you play with your policy that you have until a terminal state is reached. Once a terminal state is reached, you remember which value you got and where you led, what was your last state, and you start backing up the values that in the tree has been relevant for you to reach that final state. And those are the measures that we really care about, which is how many times we have been in that situation, so state and action, and what was the value that we got at the end of our rollout. Great. Now, how do we define, say, how do we explore new possible actions for each possible future state? Well, I mean, as humans, sometimes we really like to get drunk and we try things at random and eventually we get a good memory sometime. But, you know, and this is actually called epsilon grid. I mean, I'm not joking. It's a method that is really used, especially in deep Q learning. We would like to do something, say, a little bit more interesting. And we might want to try actions that we feel like they are right. What does it mean to feel they are right? It means that we want to try action that we believe that could somehow improve our situation. Or in other words, we would like to try action for which we are uncertain about the value of this action. And that's what Bandit does. I'm not going to go into the detail of it, but this is somehow, if you can think of it as a premium that you give to the value that you estimate with the Monte-Carlo tree search, and it's going to prefer action that, I'd say, has been explored less in a specific situation. It's going to prefer action that's been explored. It's going to, say, give less premium to action which are more certain about their outcome. And I think I'm done. Manuel, you're up.
Thank you, Simone. I'm sorry for the code, but there was something more interesting behind. So another main pain problem within AlphaGo and Go as the game of Go is that we have a policy, which is something that tells you, what should I be doing now? But we cannot understand how good is my policy, because to understand the policy, you should play against Lee, which is a person, and as a person, it's very slow. So we don't want to do that. But how can we do that? If we cannot use another computer, which will be fast enough, but our point is to find a computer good enough to beat us, we cannot use a human, because they are too slow. So the only option is to clone yourself. Clone yourself and fight against yourself. As you are fighting, another copy of yourself is watching the fight and wondering what could have been done better, what could have been done worse. So the next iteration, you look at what happened and then improve over that. This is what happens when you use this approach with sumo, and they're very funny, especially the ends, because no human will ever fight like that. But that's more efficient because it gives you more stability. But we are talking about AlphaGo, which is a more boring game. It's a board game. There is no fighting, nothing interesting. So let's go to the Python code. We started the environment. We use our policy to pick what to do next, given what we are seeing. And then we let the opponent play. We look at the opponent action, we take everything, put it in a box aside. This is our experience. And in the future, we are going to improve on that. But for now, we are just fighting. Your first version is your player against the opponent. You just put everything in this box. The other key insight in AlphaGo is to using deep learning to better represent features. Features in machine learning are abstraction of the state. If I were to classify people or animals, I would have very simple features as like lines on the first layers in a convolutional settings, and then higher level would point out faces, and even higher level will tell me where are cats and so on. But since we are in Alpha 0 and our goal is not to find cats, but is to win, to win better, we want to find the best representation to have an idea about what's going on. Because over this, we have to understand our policy function, which tells us how to play, and our value function, which tells us how good things are going. The key element of this network is the residual network, which is nothing except of a bunch of deep learning with the output concatenated to the input of each layer. With this approach, we can put many layers. Okay, there are going to be many layers. It's 40 layers, one on top of the other. And each one of these things is million parameters. So we have millions of parameters, everybody trying to understand how good the game is going, how good you're playing. And on top of everything, we are in this special layer, we are going to have an idea about, is the opponent being offensive? Should I play defensive? There is no more information about pebbles, pixels, nothing. This is abstract thinking, as far as we can get. And the last layer, the value add and policy add, are the mechanisms which are going to move us from the high-level representation to a number which is +1 or -1 if you're winning or not, and another number which points out the best action to take. They are very simple deep learning networks, because the most important part is the fully connected layer, which is basic, given the hugeness of the network. Even the policy add is as simple. And everything else is aimed to make our model have a better idea about what's going on. We want to minimize our idea of winning or losing and the final result of the game. And also not to change our mind too fast. Our mind too fast. Because if we change too much between one iteration and the other, we are going to be undecided. Okay? So we want to change a little by little and then play against your past self. If your past self wins a lot, then your improvement was not as important as you were thinking it would be. If you beat your past self, it means that you improved a lot. Let's go to the code. Can the Regia help us? Can you click it? Yeah. Okay. You need to scroll it down. We define an environment, which in this case is an Otello game, because my computer will not handle Google level deep learning. I'm sorry. And then we are going to define a policy search tree, which is aware of the environment it's working in and of the neural network, which is going to be our decision-making procedure. And we store our cache of experiences in a queue. And then, can you scroll down a little bit? Okay, thank you. And then we are going to do, for a few times, some games, like 100 games, 1,000 games, against ourselves. So all the information, as I showed you before, in this point, and then instantiate one exact copy of yourself and train yourself on the past experience. In this case, after this, we are going to fight against we are going to put yourself of this moment, the improved one, against your old self. And if you were worse than your old version, then you kill yourself, and your past self comes back from the past. This is the core of the algorithm. Now we maybe can go over the deep learning training. No, that's all. No, that's the right one. It's okay. It's okay. No, it's not. Yeah. So this is PyTorch. If you have followed the PyTorch introductions, we define an optimizer. In this case, it's Adam because it was the best optimizer I could find. We set the neural network as in training mode, which is not relevant to understanding the structure. And then we do the usual learning procedure as if it were a classification. But we are just trying to scroll down. We are just trying to minimize the previous losses. Don't change too much, but improve your evaluation. Because in this kind of algorithm, we don't care about the policy itself. The policy is based on what we think is going to happen. We are going to try to do our best, except for exploration. But other than that, there is just the trying to understand what's going on. And it's as simple as 2 pages of Python, but it's a very powerful concept. So yeah, it's right. Right arrow. Okay, thank you. So if you have some question, now is the time. Okay.
So happy to go back and check on specific slides and formulas or concept that you haven't catched.
Yeah.
Give them up. Let's do this.
Okay, in one of the slides before, there was the concept of taking the average of the value that you got from playing the games. But I've experimented a bit. For example, maybe this is okay for Go, but there are positions in chess in which if you take the average, make random moves, I take the average is very good. But you are going to be mated in one, because there's just one move that kills you. So taking the average maybe is dangerous.
You mean this average? Okay. Yes. Okay. So. Okay. Let's give that to the people and. No, because otherwise the people and it's for the recording.
Okay. The problem is that there are some position in a few, homemade experiments or whatever, but in which if you take the mean value using random moves or with a bad policy moves, the value you can extract is very, very wrong, because the average is good, but there is one move that is going to kill you, and so you are sort of getting a wrong evaluation from the position.
Okay.
Because the value maybe it's different from Go. I don't know. I'm not a Go player, so maybe the position cannot change.
Sure.
But in chess, just a little mistake, you can be from plus 20 to minus 20, or checkmate.
Sure.
So it's very unstable as position. So I don't understand how this can be, because of course it works. So I mean, even in chess, destroyed the best program. But I don't understand how this, if this can be a problem, or how this mean.
Okay. So, okay. So first of all, AlphaZero has been applied also on chess and shogi. Both of them has been beaten. The idea is that, I mean, this is called mean, but it's an estimation of an expectation, which means that, in other words, it's just a way of measuring how good is your policy working out and how good you can predict the value of your state. Now, by definition, the way the value of the state, when you are going to evaluate a state, is going to take into account what you can do in the near future. Sorry, not only in the near future, but until the end. That's why it's very hard to build an evaluation function. So even if it's the mean, this takes into account the capability of behaving. Okay. Anyway, so it's the capability of behaving optimally until the end using your predictor. So it's not really related to the kind of game that you play. And that's why it also works in chess and shogi. It's more from an algorithmic point of view. The other interesting thing is that they've been running a post-analysis on chess, on AlphaZero, and what they found out is that it doesn't get any concept of points, for example, but is much more interested in placing the pieces in a good position on chessboard instead of capturing or exchanging pieces because of I don't know, of getting more points. And that's been really striking. For example, he's able to recover some of the most famous opening, but he doesn't, and he prefers to play on specific pieces on the board, but doesn't really understand the concept of points. Okay. Did that answer to more or less your question?
In this case, we are also considering the action. Like, we are not asking ourselves what is the average value, what is the average value from this position given that I'm doing that. So if that action, as you were noting, is a very bad action, our value will be very, very low because we are going to die often from that point on. Okay? So you are also considering what you are doing within the estimation, which makes it more stable to to problems like that. So, did it improve the answer? Yeah, as you said, it's a lot about the numbers. I showed you a network which had 40 layers of millions of parameters. That's a lot of numbers. Google can do that. I don't think we can do that.
And also the sampling is done many, many times. It's like 10,000 times you sample that, and that's give you a right estimation of the expectation.
Some other question? In order to train the system, is it necessary to show all the game or every state by state when you do the training? The input is all the moves in the game or every single moves, and otherwise how can you propagate the reward to the first moves?
Okay. So that's a very interesting question. Usually in reinforcement learning, you use the reward in order to guide your learning, and you usually get a piece of reward while you explore the environment. In this case, we don't. We just get 0 if we didn't lose, we get 1 if we win, and we get -1 if you actually lost. That's all we get. Otherwise, it's always 0. It's a very sparse reward. Yeah? And contrary to what has been expected, what has been, say, learned in the past, sparse reward actually works a little bit sometimes better than dense reward. Yeah, so you just give the whole episodes and to the learner. I think also you shuffle before training, and that's pretty much it. So you give you give a lot of those training sample. You do mini batch training on that, and your model is happy with this kind of training.
Thanks for the talk. You say that you're using a convolutional neural network for the training of AlphaGo, but how can convolution extract features for a game? Which kind of feature are you extracting with a convolution? I don't get this.
Hello? Okay. Feature analyzing the layers of a neural network that huge is complex, so nobody did it yet. But we can make some informed assumptions, something, given the image, the behavior of this kind of network in other domains like image recognition and so on, or in robotics. What is it doing is trying to understand an abstraction which makes you understand the game better. So in Go, it could be like, how offensive is the game, okay? Or something like, do I control this part of the board? That's important. What is not important is the first, what you can see with your eyes. Like, is this pixel black or white? Doesn't matter, okay? On the higher level. On the lowest level, you get like, is this a circle, like a pebble, or that's a line of dividing the field or something like that? It's okay? You got it?
Yeah, so there are a couple of things to notice. The first one is that the game of Go is really based on patterns on the board. So depending on how you have stones placed, that can give you a hint on what your player is doing. Now, how you find patterns in some inputs? Well, you try to convolve them and see what kind of patches there are there, and what you can extract, and what kind of information you can extract from that. That's why they use convolution instead, for example, on other kind of network like LSTM, because you don't need you really don't need any memory. Although we say it's fully observable, it really is not, but say you really read a little bit of very, very little memories, and the LSTM, for example, wouldn't really work in this case. On the other hand, with convolution, you're able to extract those little patterns in part of the game, and this is more or less true for many board games, the same chess or shogi, depending on what is happening in a specific area, a specific, say, 4x4 submatrix of your board. You actually can get what's going on right there. Okay. Another thing that actually they have done is that it's, for example, they added a little bit of exploration noise in order to choose action on top of what I described, and the reason is because while in Go you play just on a very small subset of your board, in chess you can move the queen from one part to the other, so it's a very long move. In order to achieve that move, in order to analyze that move, you must be able to explore or to enlarge your area of exploration.
Hello, hi, thanks for the talk. I have just a question, not clear. Are you actually using the network on an image of the board, or are you using a representation, so a grid that is as large as the board?
It is a representation of the board, but in theory there is no difference. It would be just more layers to abstract the board. Yeah. The point is that it's not interesting to abstract the board itself, because it's a clear mapping, let's say.
Hello. My question is out of curiosity, like, for example, due to the nature of stock fees that you mentioned, since it just searches like the possible tree of moves and takes the best one. Like it's been used to play against some grandmaster players, like playing with thoughts for the computer, for example, starting with less pieces. But I was wondering, like, if this approach will be also possible to use, like, to play against a human using different starting positions. Since for training with itself, it's always like from the starting position without pieces, I guess. So, like, could this approach be used to play, like, for example, I say I want to play against the engine, let's say, but I want, let's say, no rooks for the computer. Like, it will behave like playing smart moves, or will it fail because it's not able to compare it against its training process?
No. Of course, you can start from random point, and you can move on from there. It's not linked to any specific let's say starting position. There is a fundamental difference between what has been done in Stockfish and what is done here, and the fundamental difference is exactly Monte-Carlo's research. So, in what you do in Stockfish is you use this kind of minimax criteria. So you want to maximize the value among the leaf, but minimizing the risk of picking the wrong leaf. While instead here you try to estimate using sampling. What you try to get a value using sampling regardless of placing the best move on a specific point, but you want to behave good on average, just to get also back to you or an expectation.
Question?
Sorry, another clarification. I didn't get one thing. When you play Go, and you use a convolution with a static fixed dimension, you are analyzing just a small portion of the space of the chessboard. So it's sensitive to the dimension of the convolutional, or, I mean, if you increase the convolutional kernel, there is a difference, or more or less the same results because you get extraction in the next layers.
For Go, as before, we don't know because we are not Google. For other kind of game, of course, yeah, there is, because as the convolution grows bigger, you have a smaller invariance to the position, okay? But you are able to look at more stuff together, okay? But you are also messing things up, okay? If I have a kernel of a very small kernel, all the local information will remain there. If I am averaging or doing something more fancy over a big space, it's hard to pinpoint one single pebble, okay? And that's happening in the highest layer. So you really almost always want small convolutions, and a lot of them on top of the other. If it was important to have larger convolution, then they will fix each other, okay? There is some theory, but it's going to be boring.
Last question?
Yes. Do you see an application of, you have always applied this to let's say, games that you have the full context, right? Okay. So where you see the full board, okay, both my let's say, a play and the opponent play. So you have the full vision of what's happening. Do you think that this can be applied? I'm a big fan of StarCraft, for example, or you have Fog of War. So you don't see what the other player is doing. Okay.
Okay, this is a little bit of, okay. So there's a whole theory of, and there's a whole, say, bunch of methods that fall under the umbrella of partially observable MDP, or Markov decision processes, which is the model behind reinforcement learning. And the basic idea is that instead of observing the full state, you just receive noisy observation from the world, partially. So, for example, a part of the screen is black, just to give you an idea. And you start building an estimation of where you could be in the world. And that's actually it's a full there's a lot of literature on that, and I'm also strictly involved on the research on that kind of topic. And yes, definitely including partial observability in the game can certainly be will be harder, but at the same time, what you can think of is that in some cases, not in all of game, it's enough to have some history or some memories of what you've done in the past to get a good estimation of that. And that has been used, for example, in AlphaGo as well, has been used also in Atari. Back then, I used to stack 4 frames, and there was some sort of memory. And we will also probably be able to follow up on your question in a few months, because we are. Can I say that? Or okay. So we are planning to apply this method on Hearthstone. I don't know if you know the game. So hopefully we'll meet next year. We're gonna tell you about if we will be able to beat the best human in Hearthstone. Okay, we are going to be the best human Hearthstone. If you want to start trying with our AI, get us our contacts, and we'll be able to let you play.
So the time is over, and thank you both, Simone and Manuel.